Today, I'm going to talk about why functions are vectors and how we can abuse this connection to understand important mathematical constructs such as Fourier series. Many people think that math is about numbers and computation, but this is actually wrong. Math is about patterns, and specifically, three things about patterns: the discovery, when we stumble upon their existence; the how, when we show their existence; and the why, when we understand their existence. There is a fine line between the how and the why of these patterns. The how is about verifying the existence of patterns with proofs. The why is about examining the underlying mechanics of the mathematical objects at play to try to discover what features of those objects lead to what we know is true. Both steps are important to math, but too often people stop at understanding the how and don't make an effort to understand the why. Shame on them. Personally, I don't think someone's understanding of a pattern in math is complete until they understand the why. I'm going to use Fourier series to illustrate this point. If we accept certain facts to be true, I could give a quick 2 to 3 line derivation of the formulas for it. At the risk of sounding like your least favorite mathematics professor, thanks to this derivation, the how of the Fourier series is trivial. But this derivation misses the why of Fourier series, why the underlying mechanics of Fourier series lead to the formulas we know are true, and this requires substantially more buildup. But I think the buildup is worth it for two reasons. One, the why of Fourier series provides a narrative for the derivation that makes it easier to explain simply to someone with no math background. It allows you to be more empathetic. And two, the why of Fourier series leads to more easy generalization of its core pattern. If you came to this video to learn what Fourier series are, this video can absolutely help with that. But it is not the central point of this video. The central point is to demonstrate the utility of exploring the mechanics of mathematical objects to tease out the causes of certain patterns. The utility of exploring the why. I want to introduce you to what Fourier series are so that you are aware of what we are building up to throughout this video. Fourier series are linked with the idea of periodic functions, so let's talk about those first. A function is something that takes in inputs and returns an output. For example, the function x plus 1 takes a numeric input and adds 1 to it to get its output. To simplify intuition for periodic functions, we can think of the inputs as time and the outputs as the values of the function at certain times. If this is the case, then a periodic function is a function whose outputs repeat as time progresses. If f of t is a periodic function, then there is some length of time p such that f of t equals f of t plus p for all values of t. This value p is called f of t's period, but p can actually have multiple values. For example, if a is a period of f of t, then so is 2a. By definition of the period, we know that f of t equals f of t plus a. But if we reapply this identity to f of t plus a, we get that f of t plus a equals f of t plus a, which is just f of t plus 2a. This produces a new identity that tells us that f of t equals f of t plus 2a, and so 2a is also a period. The smallest value of p that satisfies this equation is called the base period of f of t, which we usually label with a capital T. And every one of a function's periods is a multiple of its base period. The two most well-known periodic functions are sine of t and cosine of t, which are functions with a base period of 2 pi. Their graphs look like this. Notice how they have a continuously repeating pattern in their graphs. In fact, if we make a horizontal arrow of length 2 pi and put its starting tip somewhere on the curve of these graphs, the other tip will always hit somewhere else on the graph. This is the same thing as saying that these functions' outputs repeat every 2 pi, just shown graphically. Meaning both of these functions' periods equal 2 pi. The reason we can tell that 2 pi is its base period is that there is no horizontal arrow smaller than this one that would satisfy such a condition everywhere. Even though we can make an arrow of length pi that satisfies this property in some places, it does not satisfy it everywhere, so pi can't be a period of sine or cosine. Pop quiz! You better have been paying attention or else I'll know when you fail this quiz. And no rewinding, cause that's cheating. I'm watching you. Okay, here are 3 different graphs of functions. Try identifying which one is periodic and its base period. I'll zoom into each of the graphs just in case you're on your phone or something and need a better view to answer this question. Feel free to pause the video here and take some time to think about it, but still no rewinding. Are you done? Okay, let's discuss. The answer is, drumroll please, this first one. If we take a look at it, we can make an arrow of length 2. And if we put one of the tips of that arrow such that it touches anywhere on the graph, the other tip will also touch the graph, which means it's periodic. The length of this arrow is the base period of this graph, since no horizontal arrow smaller than it would be able to touch 2 different parts of the graph at the same time. That means the base period is 2. This one is not the graph of a periodic function, because even though some of its output values repeat, it is not in a repeating pattern. If we try the arrow test from before, it almost immediately fails, much like me in Super Smash Bros. This one is not the graph of a periodic function either, because even though it crosses the x-axis periodically, the peaks of the functions do not occur at consistent heights, so the arrow test fails since one peak is higher than the other. Hopefully, this little quiz helped to clarify any sort of questions you had about periodic functions. If not, feel free to ask away in the comments, and I or someone else can try to answer. But it is important that you understand this now, because this idea of periodicity will be used in a key way later in this video. So if you don't, take some time to pause and ponder. I hope that's not trademarked. Now, imagine we have a periodic function, f of t, with a base period of 2 times L. We'll say that the base period is 2L because this will make the math easier down the road, which I'm sure everyone will appreciate. By definition, that means f of t equals f of t plus 2L for all values of t. Then it turns out that there is a sum of a constant and an infinite sum of sines and cosines that equals this periodic function. This sum is referred to as the Fourier series of f of t. Okay, I know I just threw up a bunch of scary symbols on the screen. Let's take a deep breath and break down all the symbols. This symbol represents that we're repeatedly summing some values. This n equals 1 means we are starting the sum by adding the terms where n equals 1. So the first terms that we would add would be this. Then we add the terms where n equals 2. So the second terms would be this. For the sum, you repeat this process of incrementing n by 1 and adding the associated terms until n equals whatever value is at the top of the symbol. In this case, the symbol at the top is infinity, which means we are repeating this process an infinite number of times. You may also notice that the inputs to the sines and cosines are being multiplied by a constant, n times pi over L. This is to ensure that all the cosine and sine functions have a period of 2L. Remember, sine and cosine naturally have a period of 2 pi, but we need this function to have a period of 2L. If we pick cosine and sine functions that don't have a period of 2L, then this sum won't repeat every 2L, so it won't be possible for the sum to equal the function. Finally, these two values in red are just some number that we're scaling the cosines and sines by, and this one is a constant. Essentially, what this sum is doing is taking all sines and cosines with a period of 2L, scaling them, and then adding them to a constant to reproduce the function. See? That's not so bad. There are actually equations for the value of the constant and the coefficient from each of the cosines and sines, which are these. The long s in this expression is notation for something called the integral of a function, which can be thought of as an infinite sum of the function's values over the intervals specified by the top and bottom numbers next to the s. And this dt right here actually has a meaning, but for the purposes of this video, you can think of it as just part of the notation. You put a d and then whatever variable. Just as an example of how these formulas might be used, let's say we have the following periodic function. It equals -1 over the interval from -pi to 0, and 1 over the interval from 0 to pi, and then this pattern repeats everywhere else. Thus, the period of this function would be 2 pi. This is how you might write such a function in piecewise notation, where the rem function is just the remainder when the number is divided by 2 pi. If we apply the Fourier coefficient formulas to this function, we get this sum as the Fourier series of the function. This notation just means we only sum for odd values of n, starting from 1 and ending at the top number. And we can actually check that this sum converges by plotting the sum. This is the plot of the first term in the sum. And this is the plot if we add the next non-zero term to the sum. And as we increase the number of terms that we include in our plot, you can see that the graph of the Fourier sum gets closer and closer to the graph of the actual function. And with an infinite number of terms, it exactly equals the function. You can go ahead and try this for yourself with your favorite graphing calculator, but Lord help you if it's a TI-83. So that is what Fourier series are and how to use their formulas. But that raises the question, where do these formulas come from? And as it turns out, we can build some useful intuition for where these come from by thinking of functions as vectors. Before we move on though, feel free to pause here and take a moment to digest what I just said. We will be building up to these formulas in this video, so it's important that you at least understand what Fourier series are at a basic level so that you aren't caught off guard when we revisit them later. A vector is a list of numbers. Pretty simple. It can have as many or as few numbers as you want. We can represent vectors with two numbers as arrows in a plane. If we let the first number specify the x-coordinate of a point in this plane, and the second specify the y-coordinate, and we draw an arrow from the origin to that point, that arrow is a visual representation of the vector. We can do the same thing with vectors with more numbers if we add more dimensions to our visualization. But I won't be doing anything above 2 dimensions because PowerPoint. We can also change the numbers in the vector to change the arrow. We can make the numbers negative, rational, or irrational. We can even make one or both of the numbers 0. If all the numbers in the vector are 0, we call that vector the 0 vector. Vectors are also unchanged by translation. So if we move this vector here or here, it would still be 1, 2. In fact, we don't even need to have the vector on a grid. As long as we know what units we are using to measure distance, we know that this vector is still 1, 2. We can also do some basic operations on vectors. We can multiply a given vector by a number by multiplying each of the numbers in the vector by that number. This is represented visually by increasing the length of the vector by a factor of the number, but keeping its direction the same. This process is also sometimes called scaling the vector. We can also add or subtract vectors, which is done by adding or subtracting each of the components. Addition can be visually represented by putting the tail of one arrow at the head of another, and then finding the vector that touches the tip of the second vector. Subtraction can be visually represented by doing the same thing, but flipping the vector being subtracted. Alternatively, you can find the result of the subtraction by drawing an arrow from the tip of the vector being subtracted to the tip of the other vector, since the arrow being subtracted plus the arrow resulting for the subtraction must sum to the initial vector. We can represent vectors with symbolic notation like this, where we have a letter with an arrow over its head. So in this example, if vector v is 1, 2, y is 2, 1, and x is negative 1, 3, we can say that v minus y equals x. Take a moment to pause the video here and make sure this all makes sense, especially the geometric representation of vectors as arrows. This will be the key to unlocking the y of Fourier series. Now, the big question is, how could a function possibly be a vector? Well, it's not. That was clickbait, and you fell for it. Now you have to like, comment, and subscribe. Yeah. But anyways, it's more precise to say that functions and vectors are analogs for one another. One way to think about it is that a vector can be thought of as specifying a function. Let's say that for any given vector, the first number specifies the value of the function between 0 and 1. The second component specifies the value between 1 and 2, and so on. Using this translation scheme, any vector can be thought of as a function. If we do this translation but backwards, we can also use this to think of a function as a list of numbers, with the first one being its value at 0, its second being at a number slightly greater than 0, and so on. This translation scheme isn't precise because with this translation scheme, a function translates to an infinitely long list of numbers, whereas vectors are generally a finite length. Also, when we translate from vectors to functions, each number specifies the value of a function over an interval, but when we translate from functions to vectors, each number specifies the value of a function at a point. However, I still think it gives an intuitive feel for why a function and a vector are analogous. A vector's numbers in different positions can be considered analogous to a function's outputs at different inputs. If we take this analogy, then the previous operations that we said work for vectors work the exact same way for functions. For example, remember that when we scale a vector by some constant c, we multiply each of its components by c. If we did the analogous operation for functions, then scaling functions would be analogous to multiplying each of its outputs by that constant c to obtain the new output for any given input, which is exactly how multiplying a function by a constant works. Also, remember that when we add or subtract two vectors, we add or subtract their matching components to get the components of the new vector. If we did this analogous operation for functions, this would mean to find the output of a function that represents the sum or difference between two functions. You would add or subtract the outputs of the two functions, which is exactly how this operation works for functions. This indicates that this analogy is pretty sound. Again, feel free to pause and make sure you're convinced that this analogy makes sense. The real reason that functions and vectors are analogous is that both have the properties that define something called an abstract vector space. An abstract vector space is a collection of mathematical objects that satisfy certain properties. These objects are called abstract vectors. The collection of all functions and the collection of all vectors are both abstract vector spaces, and functions and vectors are both examples of abstract vectors. The properties of abstract vector spaces are being shown on screen right now. Notice that the letters and numbers in bold represent members of the abstract vector space. This is generally how members of some abstract vector space are notated if the abstract vector space does not have its own notation. For the purposes of this video, it's not important to understand what an abstract vector space is. Just know that an abstract vector space is a generalization of the fundamental connection between functions and vectors, and its ability to even exist is what allows us to make an analogy between vectors and functions. However, still feel free to pause the video here to think about why both vectors and functions have all these properties, if you're curious. Now that we see that this analogy allows us to define operations for vectors and functions in an analogous manner, let's look at two useful operations on vectors and work backwards to create analogous operations for functions. The first one is the dot product. The dot product of two vectors is the sum of the pairwise products of its components. For example, the dot product of 1, 2 with 3, negative 1 is 1. Let's try to define a dot product, but for functions f and g. Remember, the analogy for the different numbers in a vector are the values of functions at specific input values. So let's multiply each value of f of x and g of x together and then sum all of these products. However, remember that with this analogy, f of x and g of x both translate to an infinitely long list of numbers. Since this is an infinite number of values, this creates a sum that evaluates to infinity, which leads to an ill-defined construct. This is a problem, but there is a way we can get around this. The way we sum the infinite values of a function is through integrals. As mentioned previously, an integral can be thought of as a way of summing a function's values over some interval. So we can define the dot product of f and g as the integral of their product over some interval, which we will call a, b. This means that the value of this dot product for functions depends on the interval we choose. This dot product of functions is actually called an inner product when it's generalized to abstract vector spaces. Let's use this notation for the inner product of two functions in the future. There are properties that inner products must have in order to be useful, which I will discuss because it will be relevant for calculations we perform later. Let's talk about these properties, and then let's talk about why the dot product for vectors and the inner product for functions both have these properties. Inner products must be linear, symmetric, and positive definite. Linearity of inner products means two things. If you take the inner product of the sum of two abstract vectors with another abstract vector, it is the same as taking the inner product of each of the abstract vectors in the sum with a third abstract vector and then summing the two inner products. Also, if you take the inner product of an abstract vector scaled by a constant c with another abstract vector, then it is the same as taking the inner product of the two vectors first and then scaling that inner product by the constant c. I'm not going to explain how we know this is true for the dot product. Khan Academy has a great video explaining this, which I will link in the description. Thank you, Mr. Khan. For the inner product of functions, this is true because integration, which is what we use to define the inner product, is a linear operator, so it has the property that the integral of a sum of two functions is the sum of the integrals of the functions in the sum, and the integral of a function scaled by a constant is equal to the integral of that function multiplied by that constant. The reason that integrals have this property is that at their core, integrals are just sums. So to illustrate these properties in actions, I'm going to give an oversimplified example to show roughly why this property of integrals exists. For an illustration of this first property, let's say that f of x and g of x have these outputs at these inputs of x, and we want to find the sum of all the values in this table. The left-hand side of this equation approaches this problem by first summing the values in the table pairwise to get all the values of f of x plus g of x at each input, and then summing all of these values together, where the second step of summing all the values in the last column would be analogous to taking the integral of f of x plus g of x. The right-hand side of this equation approaches this problem by first summing all the values of f of x and g of x to get their totals, and then summing the results together, where the first step of summing all the values down both columns individually is analogous to taking the integral of f of x and g of x individually. The reason that these result in the same value is because of the commutativity of addition, meaning that the order in which we sum terms doesn't matter so long as we are summing the same terms. And to illustrate the second property, let's say that we have a function f of x that has these outputs at given inputs, which means the overall sum of the function's values is 10. And this summing is analogous to taking the integral of f of x. If we take the function and scale it by a constant c, and then sum all of its values, its total sum is just 10 times the constant. We're taking the total sum of the values of this new function is analogous to taking the integral of c times f of x. Notice that the sum of the values of c times f of x is equal to c times the sum of the values of f of x. This is because if every value in the sum is multiplied by some constant c, then the result of the whole sum is multiplied by some constant c. And that is exactly what this property states. We can then use the linearity of integrals to make the following derivations for the linearity of the inner product. Feel free to pause here and look at each of the steps to make sure that they make sense if you would like. The symmetry of inner products means that switching the order of the vectors in the inner product doesn't change the value of the inner product. Again, I'm not going to explain how this is true for dot products because the same Khan Academy video talks about that as well. Khan Academy is out here saving my life again. But this property holds true for functions because of the commutativity of multiplication, meaning that switching the order you multiply things in does not change the result of the multiplication. I will show the derivation on screen once again, and feel free to pause if you'd like to take a look at it. Finally, the positive definiteness of inner products means that if you take the inner product of a vector with itself, it will always be greater than or equal to 0. And if the inner product is 0, then the vector must be the 0 vector. Once again, I'm not going to explain this property for dot products since Khan Academy has come in clutch with... Wait, Khan Academy doesn't have a video on this topic? Mr. Khan, how could you do me like this? I have to do this myself? Fine. Wow. It's crazy. Positive definiteness is a property of the dot product because when you square a number, it will always be greater than or equal to 0. And it will only be 0 if the number is 0 itself. If you take the sum of the numbers greater than or equal to 0, you will get a number greater than or equal to 0. And the only way for that sum to equal 0 is if every number equals 0, which would mean that the vector only has zeros and the vector is the 0 vector. And the same logic applies to functions since an integral is just a way of summing the values of a function over a given interval. The other useful operation that we will look at is the magnitude operation for vectors. For vectors, we define the magnitude of it as the square root of its dot product with itself. To define the magnitude of a function similarly, we take the inner product of the function with itself over some interval and then take its square root. This gives us the formula for the magnitude of a function over some interval. When this operation is applied to abstract vector spaces, it's called a norm. And this is axioms as well, but because we define it this way with the inner product, these axioms will automatically be satisfied, so we don't have to worry about them. Finally, similar to how the operations of scaling, addition, and subtraction had visual representations behind them, the dot product and magnitude operations for vectors also have geometric meanings. I want to talk about them here because looking at what these operations mean for vectors will give us insights into what they mean for the parallel operations on functions. The magnitude of a vector can be alternatively calculated by computing the length of the arrow representation of the vector. For the vector 1, 2, we can use Pythagorean's theorem to do this. We can draw a right-angled triangle like this with a base of length 1 and a height of length 2. Using Pythagorean's theorem, we get that the length of the vector, which is the length of the hypotenuse of the triangle, is the square root of 1 squared plus 2 squared, which is the square root of 5. However, you may notice that this is also the same operation as taking the dot product of the vector with itself and then taking the square root, which is why these two formulations for computing the magnitude are equivalent. What this indicates is that the norm operation for functions is roughly a way of thinking about the size of a function's outputs over a given interval. On the other hand, the dot product can be calculated alternatively by breaking up one of the vectors into the sum of two different vectors. One that is parallel to the second vector, which I will call P, and one that is perpendicular, which I will call Q. The vector parallel to the second vector is called the projection of the first vector onto the second. It is also known as the component of the first vector in the direction of the second vector, because it is the part of the first vector that can be accounted for by a scaled version of the second vector. Then, to calculate the dot product, we multiply the length of the second vector by the length of the projection of the first onto the second, which is the same as multiplying their magnitudes. Finally, we make the dot product positive if the projection points in the direction of the second vector, and negative if it points opposite the direction of the second vector. Let's call theta the angle between the two vectors. Then using trigonometry, we can obtain this formula for the dot product. I'm not going to explain why this formula gives the same answer as the previous formula we used for computing dot products, but I will link two videos in the description explaining this. One is by 3 Blue 1 Brown, where he gives a geometric justification for why these are the same, but it does require some prerequisite knowledge of linear algebra. The other is by Linda Green, where she uses vector mathematics and the law of cosines to derive this formulation. Thank you to Mr. Sanderson and Miss Green. This formula tells us that the dot product tells us whether one vector has a component in the direction of the other vector. In other words, the dot product tells us whether there is a part of the first vector that can be accounted for by a scaled version of the second vector. If the dot product is positive, it means that there is a part of the first vector that can be accounted for by the second vector scaled by a positive number. This also means that the angle between them is less than 90 degrees. If the dot product is negative, it means that there is a part of the first vector that can be accounted for by a second vector scaled by a negative number. This also means that the angle between them is greater than 90 degrees. If the dot product is 0, it means that there is no part of the first vector that can be accounted for by the second vector. This also means that the angle between them is equal to 90 degrees. What this indicates is that the inner product can be thought of as a representation of whether one function has a part or component of it that is a scaled version of the other function. It's okay if you aren't sure what this means yet, because these ideas will be clarified in the next section of the video. Okay, this has been a lot of uninterrupted and super heavy math dialogue just dumped on you, so feel free to pause and think about the things that we just did. Make sure that you feel like the connection between functions and vectors makes sense, and that the inner product and norm constructions seem like reasonable steps to take, because these operations will be the core of this video. And yes, I did skip the pop quiz for this section, but don't worry, it'll be back. Now, let's start talking about the way we will use these concepts in this video. Approximations. We can approximate one function with something called a linear combination of other functions over specific intervals. A linear combination of mathematical objects is any sum of those objects where those objects are being scaled by some constants. So as an example, this would be a linear combination of functions f of x, g of x, and h of x. We can actually use linear combinations to create approximations for other functions. For example, let's take the simplest case and say that we want the combination to consist of one function. Say that we have two functions, f of x and g of x. Let's also say that for some reason, we want to approximate f of x as a linear combination of g of x, perhaps for ease of computation. And we specifically want this approximation to be as good as possible over the interval from a to b. What value of this constant c will provide this best approximation? When we do approximations like this, we often say that we're fitting the function g of x to f of x. And at first glance, this seems like a very difficult question to answer, mainly because it seems very poorly defined. How should we define the best approximation in this context? To see how, let's switch from answering this question with functions to answering a proxy question with vectors. Let's say we have some vectors v and x, and we want to approximate v as a linear combination of vector x. Another way to frame this question is that we want to find the multiple of the first vector x that is as close as possible to the second vector v. How do we define closeness in this context? Let's subtract the multiple of the second vector from the first and call this the error vector, e. Let's define the distance of v from the multiple of x that we're approximating v with as the length of this error vector, which is also its magnitude. And to make the scaled version of x as close as possible to the original vector v, we want to find the value of c that minimizes the length of this error vector. Now that we've defined the quality that determines our best approximation, how do we use math to find it? Well, as it turns out, the length of e is minimized when the error vector is perpendicular to x. Why? Think about it this way. If the error vector is not perpendicular to x, then there is some component of the error vector that can be accounted for by a multiple of x. We can add this component to the multiple of x by adjusting the coefficient c, and this removes that component from the error vector and thus shrinks the error vector. So if it's not perpendicular, we can make the error vector smaller. This also works if the component points in the opposite direction of x. We would just have to decrease c instead of increasing it. In other words, if the error vector is not perpendicular to x, there is some component of the error that the multiple of x could be used to account for when making this approximation. So the only way to ensure there is no unaccounted component of the error is if the error vector is perpendicular to x. Thus, the only way that we for sure minimize the length of the error vector is if we choose the multiple of x such that the error vector is perpendicular. Because of this perpendicularity condition, the multiple of x that minimizes the error happens to be the same as the projection of v onto x. Since the error vector is perpendicular to x under optimal conditions, then the dot product of the error vector with x must be 0 by definition. Thinking about this in terms of the dot product provides another way of thinking about this problem, since the dot product of the error vector with x gives us information about the direction of the component of the error vector in the direction of x. If the dot product is positive, then there's a component of the error vector that can be accounted for by a positive multiple of x. But adding that component to the multiple of x we're using in our approximation decreases the length of the error vector. So a positive dot product means we can make the error vector smaller, which means the length of the error vector cannot be at a minimum if the dot product is positive. If the dot product is negative, then there's a component of the error vector that can be accounted for by a negative multiple of x. And once again, adding that component to the multiple of x we're using in our approximation decreases the length of the error vector. So we can't be at a minimum length of the error vector if the dot product is negative either. Thus, the only way to ensure that the length of the error vector is minimized is that the dot product of the error vector with x is 0. Now we have the optimality condition that we need to solve for c. We can substitute this expression in for the error vector. Then, using the linearity of the dot product, we get this equation. And rearranging, we get this as the required constant c to minimize the error of our approximation of v with x. Take a moment to ensure that you understand this line of reasoning and how you utilize the geometric meaning of the dot product to obtain an equation we use to solve for the optimal constant. Now let's return to our initial question about functions with this new nifty formula we've got. Let's say we're approximating f with a multiple of g over the interval from a to b. Then we can just take the formula we obtained previously for vectors and change all the dot products to inner products so that applies to functions. Doing so, we get the formula for the optimal coefficient c for this approximation. Ka-chow! Wait, that's probably a trademark. But Disney will never see this, so moving on. For those not convinced by the analogy between functions and vectors, you may be questioning whether we can actually just take the formula we obtain with vector methods and apply it to functions. And that would be a fair point to make. This derivation of the formula isn't rigorous at all, and even though it may give us some of the sense of the why of this formula, it doesn't explain how we know for sure that the methods we use to obtain the formula for vectors are valid for functions. But a neat thing is we can actually double check this formula by tackling the same problem as before, but using methods for functions instead of for vectors. But now, thanks to our computation with vectors, we know how to determine what choice of constant c is the best. If we apply the same logic as before, let's subtract the multiple of g from f to get an error function, e. And let's define the best possible approximation as the one that minimizes the norm of the error function over the specified interval. Let's write this with the inner product notation. Since the norm is just the square root of the error function's inner product with itself, and the square root always increases as its input increases, to minimize the norm, we can just minimize the function's inner product with itself. Let's define this inner product as a function, which we will call big N for inner product. Notice how this function's variable is the constant c instead of the variable x, since that is what we're trying to change to minimize the error. Then we want to find the constant c that provides the minimum value of this function big N. Now you may be wondering how we know that such a minimum value always exists, and this is thanks to the positive definiteness of the inner product. Since a function's inner product with itself is always greater than or equal to 0, this inner product's value cannot be negative, and that means it has to have some minimum value. It can't just decrease forever. Substituting for little e, we can use the linearity of the inner product to expand it to obtain this. Then, we can use the symmetry of the inner product to change this to this and combine like terms, which gives us this equation for big N. For those of you familiar with calculus, we can find something called the derivative of this function big N with respect to the constant c and set it equal to 0 to minimize the function. The way we notate a derivative is with a fraction, where we put d in the name of the function at the top, and then we put d in the name of the variable at the bottom. Don't worry if you don't know what a derivative is or why setting it equal to 0 minimizes the function, because I'll explain that in a little bit. And don't worry about how to compute derivatives either. It's not important for the intuition of this process. This gives us an equation that we can then use to solve for c. We can rearrange, then use our Twitter accounts to cancel these 2's, and then we can solve to obtain the same formula that we got before. So we showed that thinking about this problem in these two different ways leads to the same answer. But let's take a step back and think about why these two computations give us the same formula in order to gain some insight. It turns out that we can do the same exact computation that we did for functions as an alternative method for solving the proxy problem with vectors. We can just substitute the inner product of functions with the dot product of vectors. Why? Remember, we didn't use any characteristics of this inner product in this derivation other than its linearity, symmetry, and positive definiteness, which as mentioned previously is required for all inner products. Since the dot product also has these properties, these computations are equally valid when we substitute the inner product of functions with the dot product of vectors. If we do that, and then compare this method of finding this formula with the other one, we may be able to piece together why both methods lead to the same answer. Let's do that, and then let's take a closer look at the derivative of our function big N. Using linearity to simplify this formula, and then performing a substitution, you'll notice that the derivative of big N is actually proportional to the magnitude of the error vector's dot product with the vector x. What does this mean? Well, the derivative of a function tells us how the function changes if we change its variable. A positive derivative means that the function and its variable are positively correlated. Increasing the variable will increase the value of the function, and decreasing the variable will decrease the value of the function. A negative derivative means that the function and its variable are negatively correlated. Increasing the variable decreases the value of the function, and decreasing the variable increases the value of the function. A derivative of 0 means that there is no correlation between the function and its variable. Increasing or decreasing the variable does not lead to a change in the value of the function. It is also important to note that the derivative is a function of the variable c, so how the output changes as you change the variable actually depends on the value of the variable. Remember, what we're trying to do is make this function big N as small as possible, and I said that this occurs only when this derivative is 0. Why? Let's say that the derivative is positive. That means by decreasing the variable, we can decrease the function, so we can change the constant to make the function's value lower. Thus, we can't be at a minimum. Let's say that the derivative is negative instead. That means if we increase the variable, it will decrease the function, so we can still change the constant to make the function's value lower. Thus, we can't be at a minimum in this situation either. The only way for us to be at a minimum is if the derivative is 0. And since in this case the derivative of big N is directly proportional to the dot product of the error vector with x, this happens when the error vector's dot product with x is 0. But this is exactly the optimality condition we obtained when using standard vector methods instead. The way we found it there is by pointing out that the dot product tells us whether the error vector has any components in the direction of x. If it does, we can add that component to the multiple of x and remove it from the error vector, thereby causing it to shrink. In other words, if the dot product is not 0, there's a way to adjust the constant c such that we decrease the amount of error we get because there's some part of the error vector that can be accounted for by x. So the reason that these two computations lead to the same answer is because they both reach the same conclusion. As long as the dot product of the error vector with x is non-zero, there's some component of the error in the direction of x. And so we can adjust c to account for this component and thus decrease the error. Thus, the optimal coefficient is that which leads to the dot product of the error vector with x equaling 0. The first time we showed this, we used a visual and perhaps more intuitive explanation. And the second time we show this, we use an analytic, more rigorous explanation. And connecting these two allows us to explain why this optimality condition translates to functions as well. If the inner product of the error function with g of x is not 0, then there's some part of the error function that we can account for with g of x. So we can improve our approximation by adding that part of the error function to our approximation of f of x. This is the key insight that allows us to understand approximations with functions. Take a second right now to pause the video and make sure you understand why it makes sense these two approaches reach the same answer. You don't have to understand how the computations of the analytical approach were conducted, but you should understand why it makes sense that would result in this answer, especially why the derivative we ended up getting makes sense. Let's step back to Fourier series. Imagine that instead of fitting all these cosines, sines, and the constant at once to f of t, we approximate f of t with each of these functions one at a time. Let's start by just approximating this function with the cosine function where n equals 1. The nice thing about approximations with periodic functions is since these functions repeat every 2L, if we create the best approximation over any interval of length 2L, that approximation will repeat and be an equally good fit over any interval of 2L. In other words, we can choose any such interval of length 2L to approximate over to get the best possible approximation everywhere. Let's say we change the interval from here to here. Although we lose the information contained in this segment in red, that same information is replicated in this segment in green because of the periodicity of these functions. So as long as we do the approximation over a segment of length 2L, the approximation will be the same. Let's choose the simplest such interval, from negative L to L. Using the formula we just derived, we get this equation for a sub 1. We can actually evaluate this bottom integral using single variable calculus techniques, and it comes out to be L. Using this fact, we get this as the formula for the coefficients of the cosines in the Fourier series, which is exactly what the formula is for a sub 1. Let's try the same thing with the general cosine function and its coefficient a sub n. Doing the same thing again, we get this formula. And evaluating the bottom integral, we once again get L, which is exactly the formula for the coefficient of the general cosine term, a sub n. And we can do the same thing with the sine and constant functions to also get their Fourier coefficients. Evaluating these two bottom integrals, the integral for the sine function squared over this interval evaluates to L once again, and the integral for 1 squared over this interval evaluates to 2L. Using this formula that we just derived by thinking of functions as vectors, we have successfully found the values for these coefficients. So we're done, right? Wrong. Fitting multiple functions simultaneously to one function does not necessarily produce the same coefficients as fitting each function individually to the first function and then summing those individual approximations. To see why this is the case, let's do the proxy problem where we approximate one vector as a linear combination of multiple other vectors. As an example, let's say we're fitting two vectors x and y to v instead of 1. If we take their best individual approximations of v and sum them, we get this. But we can actually get exactly v using this combination instead. This shows that our approach of fitting vectors individually breaks down when we get to approximating with multiple vectors, and that also means it likely breaks down when we approximate with multiple functions as well. And indeed, we can redo the analytic computations we did previously, this time making the approximation as good as possible while approximating with two functions instead of one. I'll go through some of the details of this computation later, but if you do that, you get these equations for the two coefficients. You'll notice that I haven't explicitly solved for them yet because this form of the equation gives the best intuition for why this approach fails. But don't worry, we'll come back to explicit computations of these coefficients later. Somehow though, this flawed approach for fitting reproduces the Fourier series coefficients. Is it a coincidence, or is there something else at play? Very interesting. Let's dig a little deeper. Let's take a closer look at the equations for one of the coefficients that we get when fitting two functions to one. You'll notice it's almost identical to the one given by fitting that function individually, but there's an extra term that's proportional to the inner product of the two functions with each other. In fact, if we let this inner product equal 0, then the coefficients are exactly equal. What does this mean? Let's translate this problem back to vectors by taking advantage of the similarities between the inner product and dot product, and think about what this would mean in the context of vectors. Remember, if the dot product of two vectors is 0, it means that they are perpendicular. So if we go back to our example of fitting x and y to v, and we adjust x and y to be perpendicular, then taking their individual approximations and summing them does give the optimal combination of x and y. But why? One way to think about it is that if x and y are not perpendicular, then one has a component in the direction of the other. So if we fit them individually, then this component will be, in a sense, double counted. If this component points in the same direction as the second vector, meaning their dot product is positive, then their individual approximations will be too big and overshoot the optimal combination. If this component points in the opposite direction of the second vector, meaning their dot product is negative, then their individual approximations will be too small and undershoot the optimal combination. And it is only when there is no such component in each other's direction and the two vectors are perpendicular that their individual approximations are just the right size, and there is no double counting effect. What this indicates is that this extra term included when fitting two functions simultaneously, rather than each individually, adjusts the coefficient by subtracting a multiple of the function's inner product, which is a representation of how much of a component they share and whether that shared component points in the same direction or opposite direction. It accounts for this double counting effect. However, as long as they are perpendicular, no component will be double counted with their individual approximations. When this idea of perpendicularity is extended to vectors in more than 3 dimensions, or to functions, we call it orthogonality. So, two functions are orthogonal over an interval if their inner product over that interval is 0. And it is clear from the formulas that if two functions are orthogonal and we use them to approximate a third function, we can do so simply by taking the best approximation with each individually and then summing, since we will avoid the double counting effect. This approach also generalizes to when we have more than two functions that we're using to approximate. If none of them share any components, then no double counting occurs. So approximating each individually and summing them still gives the best possible approximation. Let's take a look at Fourier series. Since taking the approximation of the function with each of the cosine, sines, and constant functions individually and then summing them gives the best possible fit for these functions, is it possible that these functions are orthogonal? And it turns out that they are orthogonal. When the inner product of these functions are taken over the interval from negative L to L, which is the interval we use to fit, the result is 0. For those who want to see how we know this, I have a link in the description to a video by Raphael Anwar that proves these facts. I'm sorry if I pronounced their name wrong. It does require knowledge of how to integrate and an understanding of complex exponentials, but if you do understand these things, knock yourself out. Thanks, Mr. Anwar. So that means approximating the function f of t individually with each function does not produce any double counting effect, meaning summing those individual approximations produces the best aggregate approximation. That is the reason the Fourier coefficients match the formulas we found for individual approximations. And boom, that completes the y of the Fourier series. For yeah! I'm not sorry for that. Now, at this point, you may be objecting to the completeness of this explanation. Although I may have a proof of how we know that these functions are orthogonal in the description, I haven't presented an explanation for why they are orthogonal, or more precisely, why their inner product evaluates to 0. And that would be a valid criticism. As far as I know, no one has presented an explanation for why these functions are orthogonal. But I think the same can be said for orthogonality with vectors. Can anyone really explain why the vectors 1, 3 and negative 3, 1 are perpendicular, other than by definition? Okay, maybe with rotation matrices. But can anyone explain why the vectors 1, 3, 4, 2 and negative 3, 1, 1, negative 2 are orthogonal, other than by definition? I think that when we move to the realm of orthogonality, it becomes difficult, if not impossible, to offer intuitive explanations for it because the concept is more abstract and less grounded in geometry. It could be the case that there is no y. But just because there isn't currently a known y for these things doesn't mean a y doesn't exist. And I want to bring this point up here because I think it demonstrates something interesting about y's in math. There are a lot of patterns in math that don't have a known y. For instance, we know that there are an infinite number of primes, but I have never heard an explanation for why the structure of the integers naturally leads to the infinity of primes. Is there a y for everything in math? Or are there just some things we can't find a deeper explanation for, and they're just coincidental? I would love to hear your thoughts on this in the comments below. However, I still don't think this detracts from my point about the benefits of exploring the y. And to prove it to you, I will show you the traditional derivation I was talking about for the Fourier series coefficients. Let's assume that the function f of t equals the Fourier series. Let's now find the coefficient for the kth cosine term in the sum. What we can do is multiply both sides by that kth cosine term and then take the integral of both sides from negative L to L. Then we can use the linearity of the integral to break up the integral into the sum of many integrals. And we already established that all of the integrals on the right hand side evaluate to 0, except the integral of that cosine function multiplied by itself, which evaluates to L. Then rearranging, we get this as the coefficient for the kth cosine term. And we can do this to obtain equations for the sine coefficients and the constant as well. One disadvantage of this derivation for the Fourier series coefficients is that it misses the motivation for multiplying by the cosine and then taking the integral. It seems to come out of nowhere in this derivation. But with our explanation, it's obvious what this step is doing. It's taking the inner product of the function with the cosine. In fact, let's rewrite this in inner product notation and ignore the assumption that the Fourier series exactly equals the function. Instead, let's assume that we're just approximating f of t with this sum. Let's call the difference between the function and the Fourier series the error function, and then try to minimize it. As established before, this only happens when the inner product of the error function with any of the functions we're approximating with is 0. And if we rearrange this equation in the Fourier series derivation and then use the linearity of the inner product and substitute, this equation in the Fourier series derivation becomes exactly that. Doing this rearrangement allows us to see that the formula for the Fourier coefficients are optimal even when we don't know whether the Fourier series equals the function. That points to another disadvantage of this derivation. It requires us to assume that the Fourier series does equal the function. If it doesn't, then there appears to be no guarantees that this will work. And proving that the Fourier series of a function ends up equaling the associated function is actually quite difficult to prove and requires some very high-level mathematics. But thanks to our explanation, we know that it doesn't matter whether the Fourier series equals the function, since these coefficients give the best possible approximation for the function regardless of whether the function equals the Fourier series or not. But the biggest advantage of our derivation over the traditional one is most clear when we talk about generalizing the approximation formulas we've developed. Let's now return to our problem of approximating one function with another, but use an arbitrary number of functions n to approximate a single one instead. The simplest case of this would be approximating one function with a combination of two others. This is what the sum would evaluate to if n is 2. I'm just going to replace the subscripted coefficients and functions with these, just for clarity moving forward. Is there a formula for the two coefficients c and d that are optimal? Well, of course. If you repeat the calculus computation we did for one function but with two, you end up getting these as the optimal coefficients for the approximation. But if you try repeating this process for fitting more than two functions, you will quickly see that this causes the computation to become quite tedious. So instead of just waving our hands and saying that we can do the computations and calling it a day, can we instead find a formula for the coefficients resulting from fitting any number of functions to one function that is easily generalizable and allows us to avoid these computations? Now, if I showed you the derivation for the Fourier series coefficients that most resources give, you'd probably be at a complete and utter loss for how to do this. But because we did all the legwork of attributing a deeper significance to the derivation, it's probably easier to see how we might come up with a generalized formula for this. In fact, those of you that have taken a linear algebra course may be able to do so right now. And I'm going to challenge those of you who do have this background to devise a generalized formula for the optimal coefficients for fitting a series of n functions to a single one. And I'll give you 2 hints. 1. Think about the methods we use to tackle this parallel problem in linear algebra for vectors, especially the ideas behind projection matrices. And 2. The generalized formula uses determinants. I highly encourage you to tackle this problem if you have taken a linear algebra course. I had to do the same to make this video, and it took me a few days to wrap my head around it, but I did eventually figure it out, and doing so was a rewarding experience. If you just watch to find out the solution, you will miss out on the opportunity to build your problem-solving skills. So if you have taken linear algebra, seriously consider giving some effort to trying to solve this problem before looking at the rest of this video. If you do not have a strong linear algebra background, or if you still don't have any ideas of how to tackle this problem, that's okay. I'll start you off with a simpler problem that only requires you to understand what's been presented in this video so far. See, I told you I'd bring the pop quiz back, and feel free to pause at any point if you feel like you know where I'm going with this, and do some work to find the formulas before I show them to you. Before tackling this problem for functions, let's look at the parallel case for vectors. Let's once again look at the simplest case of approximating one vector with multiple by approximating one vector with the sum of two others. Let's also move to 3 dimensions so that this example makes more sense. Yeah, I did lie about staying in 2 dimensions, sorry about that. These 3D visualizations make you want to throw up as well, but we'll get to this together, I promise. Let's say we have a vector v, and we want to approximate it as the sum of multiple vectors x and y. Let's once again define the error vector as the difference between v and the linear combination of x and y. What values for the coefficients c and d would minimize the length of this error vector? I'm not going to ask you to solve for them just yet. Instead, I want you to find 2 equations that we can use to solve for the 2 coefficients. As an extra hint, the 2 equations we're looking for are linear, so they should look like this. Think about what line of reasoning we use to find the equation we use to solve for the coefficient in the case where we approximate v with a single vector instead of 2. I'll give you a few seconds to think about it, but feel free to pause and try to come up with them on your own. It will really help your understanding of the concepts presented in this video. Okay, we want the length of the error vector, or the difference between the linear combination of x and y, and v, to be as short as possible. Carrying over our intuition from the one vector case, we can say that we want the error vector to be perpendicular to both x and y. To see why, let's say that the error vector wasn't perpendicular to x. That would mean that there was some component of the error vector in the direction of x. If we add this component to our approximation and subtract it from the error vector, we get a vector that is shorter than the original error vector. So we can't be at the shortest possible error vector. The only way for us to be there is for the error vector to be perpendicular to x. We can use a symmetric argument to justify why the error vector should also be perpendicular to y. Remember, this means that the dot product of both x and y with e must be 0. If we substitute for e and rearrange the linearity of the dot product, we get the following 2 linear equations for our coefficients c and d. The reason that I asked you to just find the equations instead of solving them is that there's actually a formula for the coefficients c and d that we can use if we have the equations in this form. The system of equations can be rewritten as something called a matrix equation like this. Matrices are just grids of numbers, and they are super useful for solving linear systems of equations like this. You don't have to worry about why these equations are equivalent. It doesn't provide any additional intuition for this video. Once we have the equations in this form, to then give a formula for c and d, we can use something called Cramer's rule. I'll demonstrate how it works by using it to give a formula for c. We take what is called the determinant of this matrix and we put it at the bottom of this fraction. We then substitute the matrix on the right hand side into the first column of the matrix, since c is the first variable, and take the determinant of that matrix and put the result into the numerator. This gives the equation for c. Don't worry about how to take determinants of a matrix. Just know that's a relatively simple operation that can be done on matrices to return some number. And following a similar process for D, this gives us an equation for D as well. If you would like to see a justification of Cramer's rule, 3Blue1Brown has a video explaining the geometric intuition for Cramer's rule, which I will link in the description. Thanks, Mr. Sanderson. Wait, is it cheating to use 3Blue1Brown twice? Nah. The advantage of writing the coefficients in a formula like this is that it becomes super easy to see how such a formula would generalize if we wanted to add more functions to our approximation. Let's say that we want to approximate vector v with 3 vectors instead of 2. Then the new error vector becomes this, and you would have these 3 equations, which we can rearrange to get this system of equations. This creates a new system of equations that we can rewrite in matrix form and then apply Cramer's rule again to get these formulas for the coefficients. So essentially, we just add one row and one column to the previous matrix to account for the additional vector we're fitting. Repeating this pattern allows us to figure out that the generalized formula for the coefficients resulting from approximating one vector with n vectors is this, where we obtain C1 by applying Cramer's rule to the first column, C2 by applying Cramer's rule to the second column, and so forth. So that means that if we want to do the same thing for functions and fit a series of n functions to 1, then these would be the equations for the n coefficients. But I really want to hammer home the intuition that the vector case provided for us. Remember that the inner product of one function with another indicates whether the first function has parts of it that can be accounted for by a second function. So if we take the inner product of the error function with any of the functions that we're using to approximate f of x, this tells us whether the error vector has a part that could be accounted for by one of these functions. And if it does, adding that part to our approximation reduces the error, meaning we can minimize the error further. So the only way for us to minimize the error is if there is no part of the error function that can be accounted for by one of those functions, which means that the error function's inner product with all of those functions must be 0. This produces a system of linear equations that we then solve with Cramer's rule. Now, justifiably, you may be wondering how we know this formula still works for functions. And we can see how by doing the same calculus computation that we did before, but doing it for fitting n functions to 1. So remember, we have an error function, which is the difference between the initial function and the approximation. And we want to minimize its norm over a given interval. Its norm is the square root of the inner product of the error function with itself, so if we want to minimize this norm, we can minimize that inner product. We can substitute to get this, and this is a function which I will once again label big N. However, this time, big N is a function of multiple variables, since there are n coefficients that we're adjusting to minimize it. The same logic from before still applies. This time, we compute something called the partial derivative of big N with respect to any of the constants, which just represents how the function big N will change if we only change that constant as opposed to changing any of the other constants. Let's say that we're taking the partial derivative with respect to the kth constant, where k is between 1 and n. We notate a partial derivative the same way as we do a regular derivative, but we use these curly d's instead of the regular ones. This partial derivative is also a function of all of the constants, so how the function changes when you change one variable depends on the value of all of the variables. And just as before, we want to set that partial derivative equal to 0. We call the derivative partial because it represents only a part of the total change in the function, since we can also change the other constants. But the partial derivative still works the exact same way as a single variable derivative. If the partial derivative is greater than 0, then decreasing c sub k will decrease big N, meaning that we can't be at a minimum. And if the partial derivative is less than 0, then increasing c sub k will decrease big N, meaning that we can't be at a minimum in that case either. So the only way to be at a minimum is if the partial derivative is equal to 0. We can compute the partial derivative with respect to any of these constants by using the properties of inner products a bunch of times, and then we can simplify it with these properties again to see that the partial derivative is... Wait for it! Don't worry, it's coming! There we go. Negative 2 times the inner product of the constant's associated function with the error function. So when we set any of the partial derivatives to 0, what we are really doing is saying that this inner product must be 0 in order for the fit to be optimal. And doing this for all possible partial derivatives reproduces the system of equations we use to solve for the constants when we derive this with vector methods. As before in the one function case, we get the same answer with both methods because both methods reach the same conclusion. I just want to reiterate the main conclusions of our exploration of this topic before I end this video. What we found was that when approximating one function with a set of others, the inner product is your best friend. The inner product of two functions is an indicator of whether one function has a part of another function in it. As long as it is non-zero, there is some part of the first function that's just a multiple of the second. Let's say that you call the difference between the initial function and the approximation of it the error function. Then if you take the inner product of the error function with any of the individual approximation functions and it's non-zero, then there is some part of the error function that is just a multiple of that individual approximation function. So there is some part of the error that could be accounted for by this approximation function. And by doing so, we can decrease the error function's norm, thus improving our approximation. So the only way to minimize the error is to ensure that all of the error function is as accounted for as possible. And that happens when the inner products are all zero. And this gives us a solvable system of equations that we can use to solve for the coefficients. Also, when doing approximations, if the functions you're approximating with are all orthogonal, meaning they all have inner products of 0 with each other, then they share no components with each other. So if we approximate them individually and then sum the individual approximations, it produces the optimal approximation since we avoid double counting components. And this is why with Fourier series, fitting each of the cosines and sines individually ends up producing the best approximation, because the cosines and sines are orthogonal. And I hope that above all things is the sky, because it would be weird if it wasn't. And metaphorically, I hope that above all things, you take away the importance of exploring the why in mathematics. Doing so with Fourier series allowed us to create a narrative with it that made its derivation easier to explain and easier to generalize its core pattern of approximations. And doing so in other realms of mathematics can lead to the same benefits. So the next time you learn something new in math, or really any realm of study, make sure you don't just understand how it's true. Make sure you understand why.